Good morning, everyone. Welcome to the EasyPower Tuesday Refresher webinar. My name is Jim Chastain. I'm a Senior Applications Engineer here at EasyPower. And today's topic is the fact that there's no longer a quote-unquote low voltage exception in the 1584 standard. And just based upon the questions that we get and some of the conversations I've had, I thought it'd be a good topic to talk about and share some thoughts. And so as we start today, first of all, thank you for attending. I would like to run a couple poll questions by you, in part to get a little bit of feedback on this topic, and secondly, to inquire a little bit about your exposure to single phase. So the first poll question is, how often do your projects include, or have you relied on the low voltage exception, at least in your previous studies? And I understand the amount of heightened sensitivity to this, because in some ways it could actually impact the cost of a study significantly if there are a lot more buses that have to be brought into the analysis. So it looks like we've got a quorum here on this question, so let's go ahead and share it. Here's how people have weighed in on this, pretty evenly split. And then the second one is about single phase. How often do you include or have the requirement to include single phase in your studies? The significance there is really not a single phase model yet as far as the 1584 standard is concerned. And so the guidance is a little bit sketchy in terms of how to estimate it. And frankly, both of these topics come down to the same point, and that is there's a need for the people doing the study to be aware, if you will, or more understanding in their knowledge of the system locally. So here's how this is stacked up. I appreciate your participation. So let's jump into the discussion for this morning. Okay, so in the old standard, 1584, 2002 version, the paragraph or the verbiage that was labeled low voltage exception stated that equipment below 240 volts need not be considered unless it involves at least one 125 kVA or larger low impedance transformer in its immediate power supply. And in some other portions, the term disregard as an arc flash hazard was mentioned, and so it gave it gave some guidelines that a lot of people adhered to as far as considering doing analysis on systems that are powered 240 volts and below. With the most recent update, which was published in November of 2018, this topic has been modified, or the verbiage has been changed, and now the statement is sustainable arcs are possible but less likely in three-phase systems operating at 240 volts nominal or less, with an available short circuit current, or a short circuit less than 2000 amps. Well, at the very least, my personal opinion, this is a pretty spongy statement, and it doesn't give any clear guidance as the 2002 version did. And in some ways, this actually, I think, can be attributed to the fact that there's a growing body of knowledge on the topic, and there's some elements that of real life systems that weren't necessarily being covered by the model as it stood. So what I'm wanting to do this morning is basically look at a couple systems, look at a couple examples, and see how this applies as far as comparing the old version versus the new version, and then offering some options as far as an alternative. I mean, there is some guidance, and we'll talk about that. But then there's some leeway in terms of engineering knowledge and local knowledge of the system that can be applied, and some of it could have bearing on the cost and the discussions with the client. So let me jump into a recent example that I discussed with the EasyPower user most recently. And as I do this, I also want to, and I apologize in advance, this is a little bit of a soapbox for me. In both the 2002 version and the 2018 version, there is what's referred to as the 2-second rule. And the statement is, if the total protective device clearing time is longer than 2 seconds, consider how long a person is likely to remain in the location of the arc flash. It is likely that a person exposed to an arc flash will move away quickly if it is physically possible, and 2 seconds usually is a reasonable assumption for the arc duration to determine the incident energy. And the reason for bringing this up is that it's very much applicable to this low voltage situation. So again, let me jump into my example. And in this particular case, this is the EasyPower 1 line that has a fairly extensive 208 volt circuitry. And so as we come down and look at the calculations after we completed the 1 line, we can see the short circuit current in this lower section is somewhere in excess of 1600 amps, 1700 amps, so, and just slightly below 2000 amps in the 480 volt. No, actually, this is still the 240. So the point being, what happens to our instant energy in the calculations in the 2002 regime. So we're going to go to let's fault all the buses, and then look at the instant energy calculations. So what we see is 5 calories, here's 18 calories, and in the 480 volt section, that's for instant energy is fairly mild. So the question is, what's going on in the low voltage side, or in the 240 volt side? So let's pick out a single bus and fault it and arrange for arc flash. And what we see is this particular bus is supplied 208 volts. It's looking at this particular breaker in for a tripping device. The arcing current is less than 500 amps, and the trip time we're showing is a little over 4.5 seconds. So if we go up and look at how this file was set up under our arc flash hazard tab on short circuit options, we see that we're using the 2018 version. We're excluding the main, which is good. We're using momentary current, and we're not limiting the calculation time. So, and in fact, let me just kind of take a step back. In 2002, when we apply this, it actually, some of these numbers kind of became a little bit reduced because we had higher bolted fault current, higher arcing current at the time under this range, and part of it is the comparison of the arcing current. So back into 2018, exclude the main. We want to make sure we're using the integrated method, and we apply, and we get the 7 calorie exposure. With this case, the trip time is 7 seconds. If we go in and look at our short circuit options and apply a 2-second limit to everything under 240 volts or 250 volts, this is a circuit that's ideally suited for this exception. So now we have something in the 2 calorie range, and it's due to the fact that we've limited our calculation time now to 2 seconds. So the issue is the fact that with the lower and presumably more accurate arcing current from the 2002 model, it actually delays or prolongs the response time of our trip devices, and consequently 2 seconds is a reasonable explanation or reasonable assumption to make because of these lower currents. If we look at some of these other buses, they fall in line fairly nicely. So this is an ideal case as far as applying the 2 second rule. So bottom line here is the recommendation of 1584. It's not to ignore or assume that these are not an issue, but to basically limit the arcing time, because in fact we are going to have exceedingly low arcing current. Okay, so that's 1584. Now let me go back to my soapbox. What I found is that when people did apply this rule, even under the old standard, there was a tendency to misapply it. And that is, they being a fairly wide swath of the facility people, as I look at studies, start off with a 2 second limitation on their setup. So let's look at an example of this. And the reason, hopefully the reason I'm complaining about this will come into view. So I'm going to close this example. So I guess what I'm saying is that the process of handling the 2 second rule at least allows us to get into range of not having outlandish results. Okay, so again, here's a large one line. I've set up under my named views the area that I want to focus on, and it turns out in this 240 volt section of the plant, we find, I want to just fault this one bus, not everything in the world, we find high instant energy. So if I fault this guy, we see we have 56 calories. So the next question is, how is this set up? If I come into my short circuit options, all right, this was set up under the old standard. There were two things that jumped out at me about this particular file. One is the output was being calculated including the main, and this applies across the board. So most 480 volt systems and 240 volt systems in the US don't have a barrier between the incoming conductors and the main bus. So this was an error that initially caught my attention. But then secondly, I see that there's a limitation of 2 seconds across the board during these calculations. And even with that, we're seeing exceedingly high incident energy in a 240 volt side of the world. So the question is, how is this happening? So the next thing I would want to do is to look at the protective device, which ought to be this puppy up here, and go into my TCC curves. And what we see is the potential, and again, we're going to fault this bus. So the maximum current through that breaker is indicated by the clipping. And if I right click on that curve and insert an arcing tick mark, it shows me that the 100% arcing current is expected to be 700 or 7,700 amps, falls just to the left of the vertical band for that breaker. So in fact, the fact that we're seeing an exceedingly high instant energy has nothing to do with the 2 second rule, and in some regards is obscuring the fact that this is a miscoordinated device. So let's kind of take a step back. So that's under the old standard. Now let's look at the same thing with the new standard. So I'm going to go back to short circuit options and look at the new updated standard. We're going to exclude the main, and we're going to undo the. Now the other thing that's worth noting is that with the new standard, you want to use the integrated method because there's a recognition of the fact that over time the fault current could actually decline for one reason or another, either loads dropping off or motor contribution declining. So on large faults or long faults, the integrated method actually will end up providing some relief. So now if we apply this and go in and fault our bus again and look at the current, this is a substantial amount of current, and so it's reasonable to expect high incident energy. And if we look at that, even under the new standard, we're showing 85 calorie exposure. So 2-second limit, which we'll apply now, doesn't really do that much good. Again, what we're missing, the point that I'm trying to emphasize, is thinking by applying the 2-second standard right off the bat, we are setting up a safe condition, and the fact is we're overlooking a miscoordination of the breaker. So let's kind of come back and look at the same thing and reiterate my point. So if I pick out the system between the bus that we're focused on and the protective device and plot it, fault this particular bus, we can see that again we're clipping, in this case, at 23,000 amps, and our arcing current is not showing up. How come it's not showing up? Let's try this one more time. Actually, I want to go back. So what the tool is telling me is that this is not the device, that's limiting, and we're still stuck on our 2 seconds. So sorry about that. I have to go back and look at my 2-second option, relief I take that relief away, and now go back to our coordination and plot the TCC. So because that breaker wasn't the tripping device, it was not allowing me to indicate where the arcing current would be. All right, so by inserting the arcing tick mark, you can see the reduced, and this is another thing, the reduced arcing current is no longer a choice that the operator makes. This is built into the equations. And so in this particular case, the reduced arcing current is giving us the trip time of something over 5 seconds, it looks like, because it's where it crosses the right side. It's almost 6 seconds as far as trip time. The point being, if I left click and drag and make an adjustment to this breaker ever so slightly, now that same current will trip the device in less than 50 milliseconds, and I can see instant energy now below 9/10 of a calorie. So the point is, just automatically applying the 2-second rule is, in my opinion, not the first place to go. You really do want to understand what's going on in your system, because places where you have excessively high current, the system should be designed to take care of itself. And so it's a misguided approach to just take the 2-second rule as a first place to start. Okay, so that was a little bit of a divergence from the topic, so let me kind of go back and get back on board here. So the point is, the new standard may mean there's dozens of additional panels that need to be added to the study, and there's the potential for that to be hundreds of additional man hours, increasing the complexity of the model, and certainly potentially having more labels. Now, what I'm about to describe, well, as far as the standard 1584 2018, what we have as far as relief from that situation is the 2-second rule. And what I'm about to talk about are all alternatives, and they're not covered by the 1584 model. They fall into the territory of sound engineering judgment. And so that's where I would encourage you to have a conversation with your client about what the trade-offs are involved. And this is not a comprehensive list. This is just a way to kind of guide the conversation. One approach is to say, okay, well, let's look at what's recommended in the NESC standard, the National Electrical Safety Standard, and they show for 50 to 250 volts recommendation for PPE to be rated at 4 calories on both 3-phase and single-phase equipment. The thought being that under typical applications, in a worst case, at these voltages, you won't exceed 4 calories per square centimeter if the system's been designed and coordinated properly. So the possible option in this case would be to label anything. I guess the first place to start is if my qualified workers are going to be having their daily wear rated at a minimum of 4 calories, then I could safely label these elements in my system without necessarily going into an extensive analysis of all the different loads in these cases. That's one way of looking at it. So the daily wear for our company now would be 4 calories, and I could use a generic label for the low voltage systems as long as there's no exception to that rule, and the justification is based upon the NESC recommendations. That's one approach. Another approach, and this, if you look in the bibliography of the 1584 standard, one of the papers that's been in the public arena now for the better part of 10 years is some testing that was taken on by a couple of engineers from Merson, and they found that below 250 volts there was a lack of sustainability when we have low arcing current. And specifically, these tests were made at 208 volts, and they found that below 2,000 amps, horizontally is the available fault current. Below 2,000 amps, the arc could be established, but it wouldn't sustain itself for even 10 cycles, let alone a second or 2 seconds. Now, I think it's safe to say that the wording, the verbiage in the current 1584 standard takes this into account, and that's what allows us the 2-second limitation across the board if we need to at 240 volts. On the other hand, if I know that in fact my available fault current is much less, like in the case of that first example, much less than 2,000 amps, I have a safety factor that 2 seconds exceeds by orders of magnitude, and I have some justification for limiting that calculation time to 1 second and potentially even less. But again, what we're talking about is an engineering assessment of what my actual physical system is set up to handle. So again, I'm not making a recommendation. I'm saying there is a potential that a critical or a maximum calc time of some number less than 2 seconds based upon test results and my knowledge of what my available arc current is on those systems. Now, in some regards, I mean, one way to do that is like, well, how do you know? And that is to pick out a worst case and bracket the systems we're talking about. So in this case, in the Lang-Jones testing, at 208 volts with less than 4,000 amps, the virtually everything was extinguishing itself well within the 1 second maximum time time limit. Now, I want to reiterate, this takes us outside the realm of the recommendation of the standard. In 1584, 2018, we exclude the main breaker. We use integrated method for worst case current. And then the relief on the low voltage side of things is basically to limit the calc times to 2 seconds if high instant energy is due to long trip times. Anything that you do beyond that is based upon using sound engineering judgment as you apply it or as you understand the system you're working on. So it's not something that certainly anybody else can recommend if they don't know the system as well as you. Okay, I probably stomped all over that, but I think that's probably all I have to say about it, unless there's any questions. Thank you for attending today, and I would like to note that we've got several arc flash workshops now scheduled, along with several regional training sessions that you can access both on the website and the monthly newsletter, and the new letter as well. So let's see if we got any questions I can deal with. Yeah, so the question about single phase systems. Again, it's a engineering judgment assessment, but in essence, the standard does not cover, the 1584 standard as it stands does not apply to single phase circuits. There's no recommendation. Conventional wisdom and most people that work in doing studies estimate there's a worst case potential of using a 60% of calculating a 3-phase result for the system, and understanding that it's a single phase, apply a 60% factor, a multiplication factor, to give us a worst case estimate for single phase. Okay, the question is there a reason to use momentary current? Okay, the only reason to use momentary current, in fact, it shouldn't change anything. Okay, so integrated method. Integrated method in EasyPower takes the half cycle current and applies it to the first cycle of the fault. At that point, it looks to see if the 5-cycle current, if the fault lasts longer than a cycle, the next 8 cycles, it uses the 5-cycle current. And then if the fault lasts longer than that 6-cycle period, it uses the 30-cycle current in the integration. So now to say, is there a reason to use momentary current? Momentary current will automatically be applied to any fault that lasts less than 1 cycle. Now, so the answer is no, there really isn't any reason to use it, because it gives you artificially high. Let's bring that other way around. Because the integrated method looks at the reducing current, it should give me a more accurate instant energy calculation. If I use momentary current, we actually get a faster trip time than we would see in real life. Okay, so is it applicable for 110 volts DC? The answer is no. There is, yeah, so 110 volts. DC is not covered, again, by the 1584 model, and EasyPower uses what's referred to as the max power method, and we can cover that at a different time. Thank you all for attending today. Certainly, you're welcome to contact tech support at easypower.com if you have any issues using the tools, and I look forward to talking to you down the road. Have a good day.